This recording is a third in a set of recordings that cover the introduction to anatomy and physiology. And this is specifically going to address the concept of homeostasis. So homeostasis is when we maintain a stable internal environment. Homeo is a word that means similar. Stasis have to do with kind of staying similar. I want you to think about, though, that the reactions in our body, the processes in our body, things are dynamic. Things change. So if you look at the guy in the teeter-totter, all of a sudden you may teeter to one side, but because of homeostasis, we're going to do things to get it back so we kind of are stable again, kind of flat like you see this guy is. So we want to regulate things within narrow limits. So in the discussion of homeostasis, we got to introduce you to various components that are part of homeostatic control mechanisms. So we're going to be looking at just homeostasis in general, talk about homeostatic balance, and then we'll talk about these regulations in which we call negative and positive feedback mechanisms that are going to be involved. So some of the players that you need to be aware of is the first is you have a variable. So something that changes. Could be like temperature or say blood sugar levels. Something is going to be varied, and this could be within your external or internal environment. Then we have a receptor. Typically, we're going to refer to it as a sensory receptor. And a receptor detects those changes. And you're like, okay, something has changed, but they can't really do anything about it. But what they're going to do is they're going to send that information to a control center. And sometimes people may refer to them as integration centers. And these centers know what to do in response to a change. So often you think about the nervous system, the endocrine system. Those are usually the points that are the control centers. So somehow something is detected. The information is sent to the integration center, and it has to be sent a certain way. And actually how it's sent is referred to as an afferent pathway, because it's going towards that control center. Now the integration or control center interprets that information, it analyzes it, and it coordinates a response. And it's going to tell various effectors, which could be skeletal muscle, it could be cardiac muscle, smooth muscle, it could be glands, number of different things are effectors, and the effectors will elicit a response that is going to be directed by that control center. And that information, or I should say that effector, is kind of told what to do by that control center by means of an efferent pathway. And we're going to go through some examples, okay? And homeostatic control is something that it's a common theme that you'll hear in AMP1 as well as AMP2. Now, a lot of homeostatic control mechanisms employ a regulation referred to as negative feedback regulation. So we're going to be looking at negative feedback regulation. So for example, so we have that teeter-totter, and if there's an imbalance, something has changed. So there's some sort of stimulus that produces a change in that variable. So you have a stimulus that somehow causes a change in that variable. That information is going to be detected by that receptor. And so we're going to say here, we're going to put the sensor or the receptor here. And then what's going to happen is that information is sent to the control center. And it's sent via an afferent, that's with an A, afferent pathway. The control center figures out what to do. It's going to send that information, or it's like, this is what you need to do via an efferent pathway, which is efferent pathway, to the various effectors. And so you have, let's say, put effectors here. And what we're going to do is we're going to counteract that change. We're going to get, if we had something, say, go up, the effect is going to bring it down, so then we're back to kind of our flat line. So negative feedback regulation involves where the response is going to be reverse the changes that happened. So it's going to go back to that set point. It's going to shut off the original stimulus or decrease what's happening. And this is very, very common. So examples were how we maintain blood sugar levels. Say if you eat, initially your blood sugar levels go up, but what will happen is we have a hormone called insulin, which its job is to get the blood glucose levels back down into a narrow range. The blood pressure regulation involves negative feedback. Blood calcium levels regulation is negative feedback. What we're going to use an example of temperature regulation for negative feedback. So we're going to use that today. So let's just discuss the significance of temperature regulation, also called thermoregulation. Thermos means heat. Okay, so think of your thermos. You keep your coffee hot. So this means heat. So we're going to try to keep temperature, for us, relatively constant. So humans are homeotherms. You may have heard the term warm-blooded. So here you see a wolf. A wolf is a homeotherm. Homeos means similar. Therm means heat. We maintain a relatively constant core body temperature no matter what the external environment is. Unlike poikilotherms, like you see with amphibians and reptiles, the poikilos is a word that means varied. So you may have heard them referred to as cold-blooded. Those animals, their body temperature depends upon the external environment. Now, does cost a lot of energy for homeotherms to maintain that constant core body temperature, but we can maintain activity levels despite the fact if it may be very cold out. Unlike what you see with reptiles or amphibians, they're not very mobile, not very active when it's cold out. So what we're going to do is we're going to look at the regulation of body temperature. So here's the scenario. It's very hot out, and you got the heat, and if you're crazy and like to exercise in the heat, your core body temperature may increase. And so what's going to happen, you have an increased body temperature, and what's going to happen is the temperature of the blood is going to increase. Okay, so we have one increased body temperature, and the blood temperature will increase. And that blood is going to obviously travel to the brain. And number 3, in the brain, there is a component of the brain called the hypothalamus. And the hypothalamus contains pretty much our thermostat. The hypothalamus is the control center. And what will happen as a means of detecting that increase in temperature, because we do have receptors within the hypothalamus that detect changes in temperatures. We have heat receptors as well as cold receptors. And so what's going to happen, the hypothalamus will detect that the temperature is increased. And what it's going to do, it's going to activate what we call a heat loss center. So we activate a heat loss center. Just think about it. It's logical. We want to not generate any heat. We want to try to lose some of that heat. And what's going to happen through a number of different mechanisms, number of different effectors, we're going to cause us to lose that heat so we can get back to that set body temperature. Because if core body temperature increases too much, it can denature proteins. It can affect how your body functions. So we don't want it too hot. So what's going to happen is we'll have behavioral changes, and that involves the cerebral cortex. And I'm going to come to that in a moment. So we're going to come back to that cerebral cortex. And cerebral cortex is the outer part of your cerebrum, which is the largest part of your brain. That's involved in voluntary conscious type things. So you will consciously do things to try to minimize heat gain and maximize heat loss. So we're going to come back to that. Other things that you don't have to think about, because it happens, is that hypothalamus is going to send information via nerves. So there's going to be some neural pathways involved. The efferent pathway is going to involve nerves. And what's going to happen is you're going to have sweat glands that are going to be active. So you increase sweat gland activity. When the sweat evaporates from your body, it takes a lot of heat with it. It's a great way of cooling off. So increased sweat gland activity, that will help to lose some of that heat. Blood vessels that serve your skin, they're going to dilate. And so I'm just going to do, say, here's, you see the long section of the blood vessels, but we're going to look at it straight on. And so if that was your blood vessel there, as a result of vasodilation, say it gets bigger. The smooth muscle that lines the blood vessels are going to relax. And so the size of the diameter of the blood vessel increases. And so we get what we call vasodilation. And what happens is that increases blood flow to the skin. And you'll lose a lot of heat via what we call radiation. If you just put your hand close to someone's body, you'll actually be able to feel that heat radiating off of that person. And so we have increased sweat gland activity. You're going to have vasodilation of blood vessels to the skin that allows us to cool by radiation. You'll have behavioral changes via the cerebral cortex. So just think about what you would do if it's hot out. Well, behavioral changes: go get into the pool, cool off in some water, lay in some ice. You'll notice in all these instances, and these dogs, is they're splaying themselves out. You increase surface area. More surface area, you can lose more heat via radiation. Go find a fan. Go change the thermostat in your house. Put the air conditioner on. You're not going to want to be all that active. You're going to kind of rest. So those are behavioral changes. Ultimately, all these things would be to try to get that temperature back to where it's supposed to be. Same picture, sorry. Now, what about if body temperature decreased? So it's not real common here in Texas, but say you decided, let's go up to New York or Canada in the middle of winter, and it's really cold outside. And you're outside, you don't have a lot of clothes on, it's getting cold. So your body temperature decreases. And so with this, the body temperature decreased. Again, what's going to happen is your blood temperature, so we'll say your blood temperature is decreased, cooler than it should be. That blood circulating in your body, and it goes up to the brain, and again up in the hypothalamus, same as before, same control center, but this time it detects, hey, it's a little bit too cool. So you have the sensory receptors located there in the hypothalamus, and it says what's going to happen is it's going to activate a heat gain center. So what we want to do is we want to minimize heat loss, and we want to maximize the heat gain. And so what's going to happen is it's going to direct certain effectors and try to do things to get the temperature back up to where it's supposed to be. So again, we're going to have some behavioral changes, and we'll come to that at the very end. But notice blood vessels are effectors again. But in this case, the smooth muscle that lines the blood vessels are going to constrict. And so if we start off here, it's going to be even smaller. So the diameter is going to get smaller, and we call it vasoconstriction, which minimizes blood flow, and this would be happening to the skin. So if you think about when it gets real cold, your skin, starts to get whiter because we're directing blood away from it, because we want to keep the warm blood in the core so your core organs stay working like they should, and you're going to have less blood flow going to the skin, so you're not going to be able to lose it as much via radiation. That's what we don't want to lose heat in this case. So you get vasoconstriction. Again, your skin gets white and turn blue if it's not getting enough blood flow. This picture below it's supposed to be a skeletal muscle, and what you can do is you can start to shiver. And so when shivering, the contraction of those muscles during that shivering is going to create some heat, going to generate some heat in regards to that. And the last thing, again, the effector would be the cerebral cortex, which will elicit certain behavioral changes. So what would you do if it's cold? Well, you can increase the thermostat. Let's set your temperature instead of 68, let's set it up to 80 or something, just to get the house warmer. You can use various insulative type clothing. Some people start, just jumping up and down, doing some jumping jacks to try to increase some heat production. You can snuggle, you can spoon, and you'll notice again here, these animals in this case, they're kind of crawling up in a ball. That's actually minimizing surface area, so that's going to help to minimize that heat loss. So those again are behavioral changes. Put some more clothing on. So there's a lot of different things to try to get that temperature back to where it should, because we don't want body temperature to be too high or too cold. We want it in a narrow range. Now, we all realize where people get hyperthermia, where that body temperature is too high. Some people get hypothermia, where body temperature is too low. At some point, yes, things that happen, but we're going to do that is not what we want to happen, but it does occur. But we do what we can to try to minimize that, to try to keep that temperature in a very relatively narrow range. And so this was a great example of negative feedback regulation. You had it. Temperature went up or down. The effects was to get the temperature back to where it should. Now, another example of control mechanisms is actually positive feedback regulation. Now, this type of regulation, you see that the output enhances or exaggerates the original stimulus. So you actually get further and further away from a set point. Well, why would we need that? Well, this typically occurs in events that you have to have something that occurs very quickly. They usually typically things that could be potentially dangerous, that we need to get a response as quickly as we possibly can, but there's always some sort of counter signal that's being released that suppresses or breaks that loop. There's a definite stopping point. So we'll use this example of childbirth as an example. So when the baby's head hits the cervix, it stretches it. But that sends a signal up to the brain, and what happens as a result of it, there's a release of a hormone called oxytocin. Now, oxytocin is a hormone that stimulates the smooth muscle of the uterus. It's actually, that smooth muscle is called the myometrium of the uterus. And that's going to help to push that kid out. And as that head goes further, more stretch, that increases more oxytocin, triggers more and more powerful contractions. So you're getting further and further away. So you're producing more and more oxytocin, stimulate more and more contractions. But what's the end point? Well, once the kid is out, there's no more stretch of that cervix. That's going to end. There's a preset end point there. Another great example of positive feedback regulation in our bodies is blood clotting. That's another example. I'll write some down. If you're interested, you can look them up. But blood clotting, coagulation, is an example of positive feedback. Something called the activation of complement. And there's actually another example during the female reproductive cycle when the egg is developing early on in the reproductive cycle. There's an actual example of positive feedback regulation, but I wouldn't really go look into it now. It's fairly complicated. So most of the things that we will encounter involve negative feedback regulation. I'll just give you an example of, well, what happens if we have homeostatic imbalance? We're always trying to maintain homeostasis. So if we've got imbalance, I want you to kind of coordinate that with disease. And I'll give you an example of homeostatic imbalance is, for example, you have, under normal circumstances, you see the picture on the left, is if your blood sugar increases, hormone insulin is released into your bloodstream, and its job is to tell various tissues in your body to take up that glucose, use it as energy, store it away from later, so the blood sugar levels get back to a narrow range. If you haven't eaten, glucagon is released by the pancreas, and it does things to get your blood glucose back to a normal level. That's normal. Well, what happens if I have diabetes? So there is something called type 1 diabetes mellitus. With these people, there's a problem with the cells in the pancreas called the beta cells, and they're the ones that produce insulin. Well, they can't produce sufficient levels of insulin. So they eat, their blood sugar levels go up, but they don't have the insulin to get the blood glucose levels back down. Their body still needs energy. And the thing is, the body's detecting like, wait, I don't have enough energy. I need glucose for energy. I need fats. I need a number of different things. And so it's going to start utilizing a lot of fat for energy. End product, that could be the production of things called ketone bodies, which can lead to something called ketoacidosis. They're still thinking they need glucose, so actually glucagon levels go up, and also, and believe it or not, it actually leads to even higher blood glucose levels. But the thing is, their body's not really utilizing it, doesn't realize they can't utilize it, so it gets even worse. And so what people with type 1 diabetes mellitus, the problem is we can't utilize, or we can't tell the effectors what to do to get that glucose levels back to it where it's supposed to, because it's not producing insulin. And insulin would be the mediator that would elicit the response from the various effectors. So that's an example of homeostatic imbalance. So this is the last of the recordings over the basic introduction to anatomy and physiology. You're also going to have some recordings that cover some of the anatomical terminology and directional terminology and other concepts, serous membranes and body cavities. So you'll see those in subsequent recordings.